In this video, we're finally going to give an actual bottom-up parsing algorithm. In particular, we'll talk about SLR, or simple LR parsing, which will build on the ideas of valid items and viable prefixes that we've been discussing in our recent videos. The first thing we're going to do is to define a very weak bottom-up parsing algorithm called LR0 parsing. And the basic idea here is that we're going to assume the stack contains a contents alpha and that the next input is token t, and that the DFA, this is the DFA that recognizes the viable prefixes, on input alpha, that is when it reads the stack contents, it terminates in some state s. And there's only going to be two things that this parsing algorithm needs to do. So if the final state of the DFA contains the item x goes to beta dot, well, what does that say? That says we've seen the complete right-hand side of x goes to beta on the top of the stack, and that furthermore, everything that's below the stack still says that x goes to beta dot is a valid or a viable, is a valid item for this state, meaning it's okay to reduce by x goes to beta. So if we see a complete production, dot all the way on the right-hand side, in the final state of the DFA, then we're just going to reduce by that production. The other possible move is a shift. If we wind up in a state where x goes to beta dot t, and then some other stuff is a valid item, what does that say? That says that it would be okay at this point to add a t to the stack, and if t is our input, well, then we should do a shift move. Now, when does LR0 parsing get into trouble? Well, there are two possible problems it could have. It might not be able to decide between two possible reduce moves. So if any state of the DFA has two possible reductions, meaning it's seen two complete productions and it could reduce by either one, then there's not enough information to decide which reduction to perform, and the parse won't be completely deterministic. And this is called a reduce-reduce conflict. So again, this happens if a particular state has two separate items indicating two separate reductions. The other possibility is that the final state of the DFA, after reading the stack contents, might have an item that says to reduce and another item that says to shift. And this is called a shift-reduce conflict. So in this case, there would only be a conflict in a state where t was the next item in the input, but in that situation, we wouldn't know whether to shift t onto the stack or to reduce by x goes to beta. Let's take a look at the DFA for recognizing viable prefixes that we've been using for the last couple of videos. And in fact, this particular DFA does have some conflicts. So let's take a look at this state right here. Here we could either reduce by e goes to t if we were in this state, or if the next input is a plus, we could do a shift. And so in this particular situation, if the next input is plus, we could either shift and use this item, or we could reduce and use that item. So this particular state has a shift-reduce conflict. Now, that's not the only conflict in this grammar, though. In this state here, we have a very similar problem. Here we could shift if the next input is a times, or we could reduce by t goes to int. And so this state also has a shift-reduce conflict. It turns out that it's not difficult to improve on LR0 parsing, and we'll present one such improvement in this video called SLR, or simple LR parsing. And this is going to improve on LR0 by adding some heuristics that will refine when we shift and when we reduce so that fewer states have conflicts. The modification to LR0 parsing that gives us SLR parsing is really quite small. We just add one new condition to the reduction case. So before, if we saw x goes to beta dot in the final state of our DFA, recall what that means. That means beta is on the top of the stack and is viable, and so it's fine to reduce. Now, we do have a little bit more information. So notice that the automaton here doesn't take any advantage of what's coming up in the input. This is based entirely, this decision here is based entirely on the stack contents. But it might be that it doesn't make sense to reduce based on what the next input symbol is. And how can we take advantage of that? Well, if you think about it, what's going to happen? We have our stack contents, and it ends in a beta, and now we're going to make a move where we're going to replace that by x. Okay? And if the next input symbol is t, so remember there'll be a vertical bar here and a t following, what does that mean? Well, that means that x has to come before t in the derivation, or in other words, t is going to follow x. And if t can't follow x, if t is a terminal symbol that can't come after the non-terminal x, then it makes no sense to do this reduction. So we only do the reduction if t is in the follow of x. We just add that restriction, and that is the only change to the parsing algorithm. So if there are any conflicts under these rules, either shift reduce or reduce reduce, then the grammar is not an SLR grammar. And just notice that these rules amount to a heuristic for detecting the handles. So we take into account two pieces of information: the contents of the stack, that's what the DFA does for us, and it tells us what items are possible when we get to the top of the stack, and also what's coming up in the input, and we can use that to refine our reduction decisions. And for those grammars where there are no conflicts, meaning there's a unique move in every possible state under those rules, then this heuristic is exact, for those grammars. And we just define those grammars to be the SLR grammars. Let's consider how things have changed for our running example, the deterministic automaton for recognizing the viable prefixes of the grammar we've been looking at for several videos now. Recall that we had shift-reduce conflicts under LR0 rules in two states. Let's look at this state first, the upper state. So here we're going to shift if there's a plus in the input. That's what this item tells us to do. It tells us if there's a plus, then the right move is to shift. And so now the question is, when are we going to reduce? Well, we're only going to reduce if the input is in the follow of E. And what is the follow of E? Well, we computed it a long time ago, but just to remind you, remember that E here is the original start symbol of the grammar, so certainly $ will wind up in the follow of E. And the other possibility for the follow of E is closed paren, because here at this point in the grammar, closed paren comes right after E. And that's the only two possibilities. So what that says now, what that means is that in this particular state, we are going to reduce if either we're out of input or if the next token in the input is a closed paren, and we'll shift if the next token in the input is a plus, and in any other situation, we will report a parsing error. And so there's no longer any shift-reduce conflict in this state, and there's always a unique move for every possible input. The situation is similarly improved for the other state. So here we're going to shift if there's a times in the input, and we're going to reduce if the input is in the follow of t. And what is the follow of t? Well, recall we computed this again a long time ago, and I just happen to know what it is. And so I'll just tell you, well, it included everything in the follow of E. So $ and closed paren are in the follow of t, but also plus is in the follow of t because of this usage over here in the grammar where plus appears immediately after t. But those are the only things in the follow of t. And so now we're going to reduce only if we're out of input or if the next input item is a closed paren or a plus, and there's also no longer any shift-reduce conflict in this state. And so this grammar is an SLR1 grammar. Now, many grammars are not SLR. Should emphasize that SLR is an improvement on LR0, but it's still not a really very general class of grammars. So, all ambiguous grammars, for example, are not SLR. But we can improve a little bit on the SLR situation. We can make SLR parse even more grammars by using precedence declarations to tell it how to resolve conflicts. So let's revert to the most natural and also most ambiguous grammar for plus and times over the integers, and we've looked at this grammar before. If you build the DFA for this grammar, if you go through and build the DFA for the viable prefix of this grammar, you will discover that there is a state that has the following two items in it. One says that if we see E times E, that we have seen E times E on the stack, and that we can now reduce by E goes to E times E. The other one will say that if there's a plus coming up in the input, we should shift. And notice that this is exactly the question of whether times has higher precedence than plus. When you're in this situation, should you reduce, thereby grouping the two e's together here, grouping the multiplication operation first, or should you shift the plus, in which case you'll be working on that first since it's at the top of the stack. So in this situation, the declaration times has higher precedence than plus resolves the conflict in favor of the reduction. So we would not do the shift, and we would wind up with no shift-reduce conflict. Note that the term precedence declaration is actually quite misleading. These declarations don't define precedence. They don't do that directly at all. What they really define are conflict resolution. They say make this move instead of that move. It happens that in this particular case, because we're dealing with a natural grammar, a simple grammar for plus and times, that the conflict resolution has exactly the effect of enforcing the precedence declaration that we want. But in more complicated grammars, where there are more interactions between the various pieces of the grammar, these declarations might not do what you expect in terms of enforcing precedence. Fortunately, you can always print out the automaton. The tools provide usually a way for you to inspect the parsing automaton, and then you can see exactly how the conflicts are being resolved and whether those are the resolutions that you had intended. And I recommend when you're building parsers, especially if it's a fairly complex parser, that you do examine the parsing automaton to make sure that it's doing what you expect. So now we're ready to give the algorithm for SLR parsing. So M is our automaton, our parsing automaton that recognizes viable prefixes. The initial configuration is going to be with the vertical bar all the way to the left, so the stack is empty. This is our full input, and we append $, to indicate the end of the input. And now we're going to repeat until the configuration has just the start symbol on the stack and $, in the input, meaning all the input is gone, and we reduce the entire input to the start symbol. So an intermediate configuration will be written as alpha omega, where alpha is the contents of the stack and omega is the remaining input. And what we're going to do is we're going to run M, run the machine on the current stack alpha. And if M rejects alpha, if M says that alpha is not a viable prefix, then we're going to report a parsing error. We're going to stop right there. Now, if M accepts alpha, and it accepts it in a state, if it ends in a state with items I, and then we're going to look at the next input, call that A, and what are we going to do? Well, we're going to shift if there is an item in I that says it would be okay to see the terminal A next. Okay, so that's just our shift move. And then we're going to reduce if there's a reduction item in the set of valid items, and the next input can follow the non-terminal on the left-hand side. So these are just the two rules that we discussed before. And then we'll report a parsing error if neither of these applies. Okay? Now, one interesting thing about this algorithm, if you read it carefully and you think about it for a while, you'll realize that this step is actually not needed. That we don't need to check here for whether M accepts the stack or not. Because this step down here, where we report a parsing error, if neither of these steps applies, this already implies that we will never form an invalid stack, that our stacks will always be viable. The parsing errors will be caught at this line, and we won't pollute the stack with symbols that can't possibly result in viable prefixes. So in fact, this error check here is not needed. M is always going to accept the stack. Now, if there are any conflicts in the last step, meaning it's not clear whether to shift or reduce in some state for some input symbol, then the grammar is not SLRK. And K, again, is the amount of look-ahead. In practice, we just use one token of look-ahead. So typically, just looking at the next token in the input stream.